Megacorp's staging environment has 9 security group rules. Production has 12. Nobody on the team can say which 3 appeared or when. And last Tuesday's deployment broke production in a way that staging has never once shown. Those environments were supposed to be identical. So how did they quietly stop matching? Welcome to Cloud Architect Path. Let's finish what that question started. By the end of this video, you'll know exactly when a scenario points to CloudFormation and when it points to Elastic Beanstalk, and why one qualifier word decides between them. We'll fix Megacorp's drift problem along the way, and both of these answers sit right in resilient and high-performing architecture's domains. Back in episode 1, we covered the always answer rule. 2 options can both be technically valid, and a single qualifier word in the last sentence quietly decides which one is correct. This lesson is a clean example of that. The split here is full control over every resource versus least operational overhead, and both answers show up across the operational excellence and resilient architecture's material. 5 terms anchor everything we're covering today, so let's establish them up front. Infrastructure as code is the practice of defining your cloud resources in template files rather than clicking through a console. Resources become repeatable, versionable, reviewable. Configuration drift is what happens when reality diverges from those templates. Someone clicks a setting during an incident, and now your actual environment no longer matches what's declared. A CloudFormation stack is the deployment unit, the set of resources CloudFormation creates, updates, and deletes together from a single template. A change set is a dry run preview that shows exactly what a template update will touch before anything actually changes. And Elastic Beanstalk is a managed platform where you supply the application code, and Amazon Web Services handles provisioning the infrastructure beneath it. So how does drift actually happen? It starts innocently. Each engineer builds an environment by clicking through the console, and each one makes slightly different choices along the way. Then comes a 2 a.m. incident, and someone adds one temporary rule to production just to stop the bleeding, and nobody writes it down. Over months, dev, staging, and production slowly pull apart, until a bug that only happens in production is impossible to reproduce anywhere else. That divergence has a name, configuration drift, and the source is always the same, clicking through the console by hand. Drift is like a game of telephone played with server settings. The first engineer sets up staging correctly. Then a late-night fix adds something to production. 6 months later, nobody remembers it. Production has 9 quiet differences from staging, and the mismatch is invisible until it bites. The antidote is one simple rule. If it isn't in the template, it doesn't exist. Every change goes through the file, or it doesn't happen at all. Here's the core idea behind infrastructure as code. Instead of a sequence of clicks, you describe the desired end state in a machine-readable file. You commit that file to version control, so every change gets reviewed and audited exactly like application code. You can see who changed the database instance type, when, and why. Because it's just a file, every environment becomes a deployment of the same template, and rollback stops being guesswork. It's a git revert followed by a redeploy, and the stack returns to the last known good state. Think about building a Lego model. If you follow the printed instruction booklet step by step, every model comes out identical, and the next person can rebuild yours perfectly. If you just grab bricks and freestyle it, every build is a little different, and nobody can reproduce what you made. Infrastructure as code is the instruction booklet. Write it once, and you build the exact same thing every single time. This isn't just a nice to have. The Amazon Web Services well-architected framework puts it plainly. Use infrastructure as code to deploy environments that are configured consistent with the controls present in production, so systems operate as expected when deployed. That's the authoritative reason code-defined infrastructure beats ClickOps. When a scenario describes environments getting out of sync, This principle is the tiebreaker pointing you toward the right answer. Amazon Web Services CloudFormation is Amazon Web Services' native engine for exactly this. You write a declarative template in JSON or YAML that describes every resource you want, EC2 instances, RDS databases, a whole VPC, a load balancer, IAM roles. CloudFormation reads that template and provisions all of it together as a single stack. Run the template in one region and you get one environment. Run the same template in another region and you get an identical second environment. And when you're done, tear down the stack and every resource inside it disappears cleanly in one command. The documentation states it cleanly. You create a template that describes all the Amazon Web Services resources you want, and CloudFormation takes care of provisioning and configuring those resources for you. You don't need to individually create each resource and figure out what depends on what. CloudFormation handles that ordering for you. That last part matters. It works out that the database has to exist before the app can reference it, without you sequencing anything by hand. Here's the whole point in one picture. At the top sits a single version-controlled template. From that one template, you deploy a dev stack, a full VPC, EC2, RDS, and a load balancer. From the very same template, you deploy an identical staging stack. And from the same template again, an identical production stack. Because all three come from one source of truth, they cannot drift apart. Configuration drift becomes impossible by design, not by discipline. Now, updating a production environment is where things get risky, so CloudFormation gives you a safety step. It works in 4 stages. First, you edit the template to describe the new desired state. Then you create a change set, and CloudFormation computes the exact diff between what's running and what you ask for. Next, you review that diff. Every resource that will be added, modified, or replaced is laid out in front of you. And only when you're satisfied do you execute. Nothing touches your running stack until that final step. Amazon Web Services describes it well. Change sets let you preview how proposed changes might impact your running resources, including whether those changes will delete or replace any critical resource. And CloudFormation makes the changes only when you decide to execute the change set. Think of it like a surgeon's checklist before an operation. You review exactly what you plan to do before the first cut, and you only proceed when the plan is right. Here's why this genuinely matters. Some property changes don't just modify a resource in place, they force a replacement, which means CloudFormation deletes the old one and creates a new one. On a database, that can mean losing your data. A change set is exactly how you catch that in advance. You see the word replacement next to your production database before you execute, and you stop. Without the preview, you'd only find out after the damage was done. Change sets rely on a human reviewing carefully. A stack policy is a harder guardrail that doesn't depend on anyone paying attention. It's a JSON document that defines which update actions are allowed on which named resources. Once you set it, every resource in the stack is protected by default. Anything not explicitly allowed is denied. So you can deny replace and delete on your production database, and a careless template edit simply cannot wipe it. One thing to be clear on, this is not IAM. It's a failsafe that only applies during CloudFormation stack update operations, not a broad access control. Picture a museum. Most exhibits can be rearranged freely, but the most valuable pieces sit locked behind glass. A stack policy works the same way. The rest of your stack updates normally, but the protected resource requires a deliberate, explicit override to touch. A conscious act, never an accidental click. That's the whole intent. Make it impossible to destroy your crown jewel resource by mistake. Let's lock in CloudFormation before we move up a level. Declarative templates provision any Amazon Web Services resource as a managed stack. Change sets let you preview additions, modifications, and replacements before you execute. Stack policies protect named resources from accidental update or deletion. And if a deployment fails partway through, CloudFormation automatically rolls the whole stack back to the last stable state. Failed deployments clean up after themselves instead of leaving you a mess. Now picture a different person. A developer who just wants to ship a web app and has zero interest in designing load balancers or auto-scaling groups. This is where Elastic Beanstalk fits. You upload your code, Java, Node.js, Python, Ruby, PHP, .NET, Go, or a Docker container, and Beanstalk provisions the EC2 instances, an Elastic load balancer, auto-scaling, and health monitoring for you. It sits one abstraction level above CloudFormation. When a scenario says deploy a web application with the least operational overhead, this is almost always the answer. Amazon Web Services puts the division of labor in one sentence. You build and deploy your applications, and Elastic Beanstalk provisions the EC2 instances, configures load balancing, sets up health monitoring, and dynamically scales your environment. That's the trade. You bring the code. Beanstalk brings and operates everything underneath it, so the operational burden of standing an environment up and keeping it running lands on Amazon Web Services instead of on you. Here's the cleanest way to feel the difference. CloudFormation is like designing your own restaurant from blueprints. You choose the kitchen layout, the number of tables, the wiring, every detail. You get full, fine-grained control over any Amazon Web Services service and any architecture you can imagine. Elastic Beanstalk is like renting a fully equipped restaurant space. The kitchen and plumbing are already installed. You just bring your menu, which is your code, and you're serving customers in minutes. One gives you control. The other gives you convenience. There's a common misconception that Beanstalk is a black box that locks you out. It doesn't. You keep full access to every resource it creates. You can SH into the EC2 instances, adjust the auto-scaling settings, pick your instance types, and customize the environment through configuration files. You're relieved of the setup and management burden, but you never surrender control. If you need to reach under the hood opens. Beanstalk comes in two flavors, and knowing both helps on scenario questions. The web server tier handles HTTP requests. It's EC2 behind a load balancer with auto-scaling, serving your public-facing front end. The worker tier is different. It pulls messages from an SQSQ and processes them, which is exactly what you want for asynchronous or long-running backend tasks. One environment runs one tier. So when a scenario needs to decouple a front end from a slow back-end process using Beanstalk, that's the worker tier doing the job. Here's a detail that ties the whole lesson together. When you create an Elastic Beanstalk environment, Beanstalk quietly creates a CloudFormation stack behind the scenes to manage the EC2 instances, the load balancer, and the auto-scaling group it provisions. So Beanstalk is essentially a pre-written CloudFormation template with an opinionated application layer on top. You get the same reliable engine underneath without ever having to author the template yourself. That also explains a real operational risk. If you change those underlying resources directly in the console, Beanstalk periodically overwrites your change because its stack has its own idea of the desired state. Always make infrastructure changes through Beanstalk itself, not through the individual services it manages. One fact that comes up regularly, both of these services are free at the service level. Amazon Web Services states it directly. There is no additional charge for Elastic Beanstalk, and the same is true of CloudFormation. You pay only for the underlying resources they create, the EC2 instances, the RDS database, the load balancer, at the exact same rates as if you built them by hand. So if a question asks whether CloudFormation or Beanstalk adds a management charge, the answer is no. So here's the decision rule, and it comes down to reading the qualifier. If the scenario wants full control over every resource, defined as version-controlled code with no drift and safe rollbacks, That's CloudFormation. If the scenario wants to deploy a web app with the least operational overhead from a team that doesn't want to manage servers, that's Elastic Beanstalk. And notice the third box. Any answer that involves clicking through the console to build the environment is always the wrong choice. Let me make that last point stick because it's the one that catches people. When a scenario describes engineers building or modifying environments by clicking through the console, that manual work is the problem in the story. It's the source of the drift. It is never the solution. Both CloudFormation and Beanstalk exist specifically to replace it. So any answer option that keeps the humans clicking is the distractor, not the fix. Before the quiz, let's clear 4 wrong mental models. First, Beanstalk does not lock you out. You retain full access to every underlying resource. Second, neither service costs extra. Both are free, and you pay only for the resources they create. Third, a stack policy is not an IAM policy. It guards resources during stack updates. It doesn't govern access broadly. And fourth, CloudFormation provisions infrastructure. It does not build or test your application code. That last one matters. If a scenario is really about deploying code through a pipeline, that's separate tooling, not CloudFormation. So here's what to carry forward. Infrastructure as code buys you 3 things: repeatable environments, no configuration drift, and safe rollback. CloudFormation gives you full control over any Amazon Web Services resource, defined as version-controlled code. Elastic Beanstalk deploys a web app with the least operational overhead while you keep resource access. Both are free, you pay only for the resources underneath. And for Megacorp, staging and production are now the same template, so drift is impossible by design. Now let's see how well all of this landed with a quick 5-question quiz. Let's start. Question 1. A development team wants to deploy a Node.js web application to Amazon Web Services. They have no infrastructure expertise and want to avoid configuring load balancers, autoscaling, and health monitoring themselves. Which service best fits with the least operational overhead? Is it A, write a CloudFormation template describing every resource and deploy it as a stack? B, provision EC2 instances manually and configure a load balancer by hand? C, upload the application to Elastic Beanstalk and let it provision the environment? Or D, run the application on a single EC2 instance with no scaling? Pause here if you want more time. This one is C. Elastic Beanstalk is the least operational overhead answer for deploying a web application. You upload your code, and it stands up the EC2 instances, load balancer, autoscaling, and health monitoring for you. CloudFormation could build the same thing, but it puts the burden of authoring and maintaining templates back on the team, which is the opposite of what they asked for. Question 2. An engineer is about to update a CloudFormation stack that includes a production RDS database. They need to verify whether the template change will delete or replace the database before any change is applied. What should they do? A, create a change set and review the proposed actions before executing. B, run update stack directly to apply the changes immediately. C, attach an IAM policy denying deletion of the database. Or D, enable multi-AZ to prevent replacement. Lock in your answer before I give it away. The right call here is A. A change set previews exactly which resources will be added, modified, or replaced before you execute, so you can spot a destructive replacement of the database before it ever happens. Running update stack directly would apply the changes with no preview at all, which is precisely the risk you're trying to avoid. Question 3. A company must ensure a critical production database managed by CloudFormation can never be accidentally replaced or deleted during a stack update, even if a template change would otherwise cause it. What's the correct mechanism? A, an IAM policy denying the delete database action. B, a CloudFormation stack policy denying replace and delete on that resource. C, a service control policy on the organizational unit. Or D, a security group rule restricting access. Think about which control acts during the stack update itself. It has to be B, and here's why. A stack policy defines which update actions are allowed on named resources during stack updates. Deny, replace, and delete on that database, and no template change can destroy it. Remember the distinction from earlier, a stack policy is not IAM. It's a failsafe that applies specifically during CloudFormation stack update operations, which is exactly the moment this scenario is worried about. Question 4. A team's staging and production environments have drifted apart because engineers make manual console changes during incidents. They want every environment identical, version controlled, and safely rollbackable. Which approach solved this? A. Document all console changes in a shared wiki after each incident. B. Restrict console access to senior engineers only. C. Take regular AMI snapshots of production. Or D. Define all infrastructure and CloudFormation templates stored in version control. Got your pick? Let's see. If you said D, well done. Configuration drift is exactly the problem infrastructure as code was built to solve. Put your infrastructure in version-controlled CloudFormation templates, and every environment becomes a deployment of the same source of truth. Drift becomes impossible by design, and rollback is just a redeploy. Documenting changes or restricting who clicks the console doesn't stop drift. It just slows down how fast it accumulates. Last one, question 5. Which statement about CloudFormation and Elastic Beanstalk pricing control is correct? A. Both services are free. You pay only for the underlying resources, and Beanstalk still gives you full access to those resources. B. Elastic Beanstalk charges a per-hour management fee on top of the resources. C. CloudFormation is free, but Beanstalk locks you out of the EC2 instances. Or D. Both services add a percentage surcharge to the resources they manage. Run the 2 facts from earlier before you answer. The answer is A. Both services are free at the service level. You pay only for the underlying resources at standard rates. And Beanstalk is not a black box. You keep full access to the EC2 instances and can customize the environment however you need. That combination, free orchestration plus retained control, is the correct picture, and it's the pairing the exam likes to test. That's infrastructure as code and managed deployments, CloudFormation and Elastic Beanstalk wrapped. The best free way to help is to subscribe. It tells YouTube to show these to more people on the same journey. Let me know in the comments what clicked. Want a different exam next? Request it below. And if you'd change anything about the pacing or the look, I read all of it. Thanks for being here. See you next time.